Okay, this is sample problem 15.6, number 1. In this section, we're looking at converting triple integrals into cylindrical and spherical coordinates. The cylindrical ones aren't too bad because we've been working quite a bit with cylindrical coordinates, and we'll cross the bridge of spherical coordinates when they get there. This one turns out to be cylindrical, and that's really their first task, is you want to look at the integrand and the limits of integration and decide whether it is cylindrical or spherical. Because I see the square root of x squared plus y squared and x squared plus y squared to the 3/2 in the numerator, I'm very tempted to make this cylindrical because those are just r's, okay? So that's the choice I'm going to make, and let's see what it turns out to be. So that's the first goal, is to kind of change our integrand and see what it'll look like once we make the conversion to cylindrical coordinates. And remember, changing rectangular coordinates to cylindrical coordinates means using the 3 conversions that x is equal to r cosine theta, that y is equal to r sine theta, and that z is equal to z. Okay. So first, the integrand, x squared plus y squared to the 3/2, that's r squared to the 3/2, or r cubed in the numerator. And then the denominator is going to be x squared plus y squared, that's r squared plus z squared. And then I know this will turn into an r to the 4th because when I replace dx, dy, dz with dr, d theta, dz, there's really going to be an extra r in there, okay? But I'll wait and do that in a bit. Okay, the other things we've got to do is change these limits of integration to accommodate the fact that we're doing this in cylindrical coordinates. So we want to see how this relates to a circle in the xy plane. So what I want to do is kind of look at what the limits on x and y do, like what's that shape going to look like. So this is the xy plane, and the x goes from 0 to 1. So we're going from 0 to 1 on the x. The y goes from 0 to x, which means it's basically mapping out the line y equals x. So this becomes the shape where our little integrand pieces are going to generate. So basically, if I wanted to convert that shape into polar coordinates, well, this would be the angle pi over 4 for theta that rotates around in the xy plane. And then the radius is a little bit trickier. So the radius I want to be 1 when theta is 0, and I want it to be equal to the hypotenuse of this guy when theta is pi over 4. And to do that, I just basically write the cosine relationship for this, that this is r, there's the angle theta, and I know that r is equal to the cosine of theta. Oh no, sorry. That 1 is equal to r cosine theta. That's better. Because I already know the answer for what the x component is. What I want to do is figure out how r relates to that in the angle. So 1, the answer, is equal to r times the cosine theta. Well, you can see I can solve for r, and r equals 1 over cosine of theta. And this should generate the radius that starts at 1. You can see when theta is 0, this is 1 over 1. And when theta is pi over 4, this is going to be 1 over cosine of pi over 4 is radical 2 over 2, or radical 2. And of course, this is a 45, 45, 90 triangle with a hypotenuse of radical 2. So this is perfect. So I can start writing down my limits for my new integral. So for x was going to go from 0 to 1. That means theta is going to go from 0 to pi over 4. So theta in the plane starts at 0 and finishes at pi over 4. And then r starts at 0, and r moves all the way up to 1 over cosine. So I'll clearly have to do the r integral before I do the theta integral, because it's going to introduce a theta function. And then the last one is z, and of course z goes from 0 to the square root of x squared plus y squared. That's 0 to r. So z will also have to go early, because z goes from 0 all the way up to r. So the order that I do these, either one of these can come first. Actually, I should probably do the z one first, because it introduces r, and then do the r one second, and then do this one third. So that's the order I'll do the integration. So the inner one is going to be 0 to r. The next one out is going to be 0 to 1 over cosine of theta. And then the outer integral is going to be the theta one, and that's 0 to pi over 4. Okay, so now I have the integral all set up. There's the argument for it, r cubed over r squared plus z squared, and then that's r, and then the order was, this first one is z, dz, the next one out is r, dr, and then the last one is d theta. Okay, so I'll integrate this first by dz, and then substitute the r in. Next, I'll integrate it by dr and substitute 1 over cosine theta, and finally integrate by theta and use the limits of pi over 4 and 0. When I do all that, I'm going to get pi over 12, which actually turns out to be the value of this integral when properly set up and integrated.